In previous lessons, we've talked about how to set up proportions based on similarity statements. So we can use similarity statements similar to this one right here to know how to arrange our proportions so that we can solve for our missing sides. Today we're going to look at what happens when we don't have similarity statements. There are two situations we're going to focus on today, the side splitter theorem and the triangle angle bisector theorem, and how it tells us how we can set up problems without directly knowing a similarity statement. So the side splitter theorem simply says that if a line is parallel to one side of a triangle, so if BD right here is parallel to the side of the triangle AE, and it intersects the other two sides, so BD intersects AC and CE, then it separates those sides, AC and CE, into segments of proportional length. So in this case, what that tells you is that I can say BA over CB is equal to DE over CD. Now, if you remember, we did a triangle that was similar to this overlapping one, and we weren't allowed to use this piece by itself. That's because we were using these two sides, and those are not split sides. Okay, the only thing that you can set up with proportions is split sides. Now, that's your if P then Q. If the line's parallel, then it splits the sides into proportional pieces. Or we can say if it splits the sides of the triangle into proportionally, then it is parallel to the third side. We won't use that as much. And then it also applies whether it's a triangle or you have multiple sides. So you can see in the picture below, I have these three lines that are parallel, and they cross these two lines, those two transversals. And so if three or more parallel lines intersect two transversals, then they cut off the transversals proportionally. Again, what we're saying is that each of these pieces are proportional, and so we're able to set up proportions. So I know this looks confusing, but let's look at it with maybe some color to help it make sense. So we've got AB over BC, so I did those two little pieces, AB over BC, and then you want to use their corresponding pieces. Well, AB matches up with DE, and BC matches with EF. And so we're able to say AB over BC is equal to DE over EF. Okay, you could also say, now these are other options, you could also say AC. AC is the whole thing. AC over DF. So in this case, I matched the whole piece with the whole piece. And then BC over EF, and you can use any combination of these. Another one we've got AC over BC, so we've got AC over BC, DE over EF. You just have to use the matching pieces, and you can combine pieces too. If I had 4 or 5 sections, I could do 3 over 5 of them. So it isn't just piece and piece. You can combine those pieces. So if we look at this example, HL is parallel to EF. And so what we've done is we have split side EH or EG and FG into proportional pieces. So EH is 9, HG is 21, FL is 6, and I want you to find FG. And so in this case, you have a couple of options. You can go back to what you know, and we can say, okay, the whole thing X over 6. Again, this is not the only option, but X over 6, so I did the whole side over the little part, is equal to the whole side. You have to use the matching piece, 30 over 9. I could find this little piece, LG, and I could do 9 over 21 equals 6 over Y, and then add 6 and Y together to get X. There are a lot of different ways that you can match up these pieces to find out what the answer is. You end up getting that, since I did X was the whole thing, you have 180 divided by 9 you get that the whole side, x, is 20. If you had found y, you would have gotten that y was 14 when you do your cross multiplying. Okay, so if you had gotten y was 14, then I would have asked for fg. So fg is x, which is 20. So we can use that same idea here. It says the farmer's land is divided by a newly constructed interstate. So here is the interstate right here, and we've got his property, and so the distances are shown in meters. Find the distance CA. So here's what I want. I want the distance from here to here. And so what I can do is I can break this into pieces. So one of the things that you might see instantly is I'm just going to call this x. Sometimes that's the hardest part. And I'm going to do 2,000 over x is equal to 2,500 over 3,000. So when you do that, 2,000 times 3,000 divided by 2,500, you get that x is 2,400. Now, notice that that is not what I asked for. That means this piece is 2,400, so you would add that to the 2,000 and actually answer the question, which is 4,400. Now, another way you could have done it is you could have called this whole thing x, and you could have done, again, any number of things, but x over 2,000 is equal to, now we need this whole piece, that'd be 5,500. So 5,500 over 2,500. Now, you could have done x over 5,500, 2,000 over 2,500. You could have done any combination. The difference then is in this case, x would have gotten 4,400 from the get-go because x would have represented the entire distance that you wanted in the first place. So you have choices for how to do this. And you can use the pieces parts of the sides that are split. Where you're going to run into problems is a problem like this one right here, is if I ask you something about EF or HL, then you can't use side splitter. You have to use the whole sides of the triangles. You can use whole and part, like y and 6. That y is the whole side LG, 6 is part of the whole FG. So you can do whole and part, but you can't do whole, part, right? You can't use the whole sides of 3 of the sides of the triangle and then part of one of them. So that is side splitter. Now, one of the things that happens is we talked about these different segments in the last semester. So we have altitudes, so QA here and UW, those are altitudes. And what happens is those altitudes, when they drop down from that vertex, they split the triangle into proportional pieces. And in fact, it breaks it into 3 proportional triangles. Okay, so then we've got medians. The median goes from the vertex to the midpoint of the opposite side. It breaks that side into proportional pieces. So now I've got those 3 triangles that have proportional pieces. And then the one that we're going to focus on is the angle bisector. QB is the angle bisector. It bisects the sides, and then what it does is it says right here, the angle bisector theorem says that the angle bisector, so in this case, this picture right here, the angle bisector is CD. See how it bisects the angle. So that is the angle CD is the angle bisector. Okay, so just put a note there. CD is the angle bisector. It separates the opposite side. So in this case, the opposite side is AB into segments that have the same ratio as the other 2 sides. What that means is that AD over DB is going to have the same ratio as AC over BC. Or you can combine those also. You can combine these 2 together. So I can combine this side with this side, and then I can do this side with this side. Okay, so it doesn't matter which one you do. You can do the side of the triangle, the piece, and the piece, or you can do the side of the triangle and the piece, and the side of the triangle and the piece, however you want to organize it. I kind of like these because they're kind of already set up. So this is how you're going to do it. Anytime you see that angle bisector in the problem, this is what's going to happen. Okay, so you need the pieces of the side that's opposite. So I have 9 and I have x. And then you need the two sides of the triangle that existed that are the whole pieces, the sides that didn't get split up. Well, if you look at this, this kind of sets it up. 9 over 24 equals x over 18. So it kind of already stacks itself up nicely as a proportion. So I have 9 over 24 is equal to x over 18. So 9 times 18 divided by 24, you get 6.75. And decimals are okay. It might cause you some concern that you might want to go and look at it just to make sure that you set it up right. Again, this is not the only way. I could have done x over 9, and then I would have to do 18 over 24. But if you notice, when you cross multiply that, you're still going to be doing 9 times 18, and you're still going to be doing times 24. Then we have this last one. Now, here's the problem with the last one. So we have our angle bisector. Here's our angle bisector. And our angle bisector is supposed to break the opposite side into proportional pieces. The problem is I don't know how big that piece is. And I need it because that's a part of the proportion when I set up my proportion. Well, so if you look at what you've got, what I know is that if I knew what x was, I would subtract it from 15, and that would give me that other piece. So if x was 10, then 15 minus 10 would give me that little piece is 5. So since I don't know what it is, though, I'm going to write this in terms of x, 15 minus x. Okay, so now I've got it set up. Again, I kind of like these because they're already nice and set up. All I have to do is use those pieces. 15 minus x over 20 is equal to x over 10. Be careful when you do this. Make sure that you multiply the entire top. It's 10 times 15 minus x. That's 150 minus 10x is equal to 20x. You get 150 is equal to 30x, or x is equal to 5. So if x is equal to 5, then I know the other piece has to be equal to 10. Okay, so we have these two problems that set themselves up. Whenever you see an angle bisector, know that you're going to be looking for the pieces of the sides that got split, and then the other two sides, the two whole sides of the triangle, and you're going to create proportions with them. And then if you've got parallel lines, your giveaway is your parallel lines. Anytime you have parallel lines, as long as you're talking about the sides that got cut by the parallel lines, you can use the side splitter theorem.